In hypothesis testing, an observed effect or difference is considered statistically significant if the p-value is less than the significance level, or if the confidence interval does not include the hypothesized value. This image shows a key challenge in hypothesis testing, that is, whether a statistically significant effect also holds practical significance. In both scenarios, the difference is statistically significant, but the bottom graph demonstrates a greater difference between the means of null and alternative distributions, which indicates a larger effect size and potentially higher practical importance. This difference is particularly crucial in large-scale studies. Because the p-value is highly sensitive to the sample size, studies with very large samples can detect even tiny or negligible effects and label them as statistically significant. Therefore, to evaluate the practical importance of a finding, researchers also consider effect sizes, which measures the magnitude of the observed effect independently of the sample size. Effect sizes are generally categorized into standardized and unstandardized measures, based on their interpretability and context of use. Unstandardized effect sizes are represented in the original units of data, such as the mean difference, regression coefficients, or risk difference. While standardized measures convert effects into a common, unitless scale by dividing a raw difference or association by a measure of variability, which allows for direct comparison of effects across studies. Let's explore some widely adopted standardized effect sizes, typically grouped into three main families: the standardized mean difference family, the correlation family, and measures designed for categorical data. Cohen's d measures the difference between two group means in terms of standard deviation, which is calculated by dividing the difference between the means by their pooled standard deviation. These are the conventional guidelines for interpreting Cohen's d values. For instance, a teacher assessing a new teaching method on math test scores found a Cohen's d of 0.45. This indicates the new method resulted in mean scores approximately 0.45 standard deviations higher than the traditional method. This suggests a noticeable positive effect that falls within Cohen's small to medium range. Cohen's d is most suitable for comparing the means of two groups when they have similar standard deviations and approximately equal sample sizes. While Hedges g is generally preferred for comparing two group means when samples are small or unequal. It provides a less biased estimate by multiplying Cohen's d with a small sample bias correction factor. Similarly, if the standard deviations between groups are notably different, Glass's delta might be a more appropriate alternative as it uses the standard deviation of the control group only for its calculation. Now, let's move on to the correlation family of effect sizes. Pearson's R measures the strength and direction of a linear relationship between two continuous variables. Its values range from -1 to +1, where negative values indicate a negative association, positive values indicate a positive association, and the absolute magnitude represents the size of the effect. These are Cohen's conventional guidelines for interpreting the magnitude of Pearson's R effect sizes. If we square the Pearson's R value, we get the coefficient of determination. This value represents the proportion of variance in one variable that can be explained by the variability in the other variable through a linear relationship. Its value ranges from 0 to 1. For instance, an R-square value of 0.36 indicates that 36% of the variance in one variable is explained by a linear relationship with the other variable. Similar to R-square for linear relationships, eta square is used to measure effect size in ANOVA. It represents the proportion of total variance in the dependent variable that is explained by a particular independent variable or factor. Its value ranges from 0 to 1. For instance, when comparing weight loss across different diet types, a calculated eta square of 0.40 indicates that 40% of the total variance in weight loss can be explained by the different diet types. This represents a substantial or large effect of diet on weight loss. In multi-factor ANOVA, when the variance explained by other factors is excluded, the resulting effect size is known as partial ETA squared. Its general interpretation is similar to eta squared. Omega squared is preferred over eta squared when a less biased estimate of the population effect size is desired. This makes it more suitable for generalizing findings to a larger population, particularly with smaller samples and in fixed effects ANOVA designs. Its general interpretation is similar to that of eta squared. The categorical family of effect sizes measures the association among categorical variables. Phi coefficient measures the association between two binary or dichotomous variables, much like Pearson's R. Its value also ranges from -1 to +1 and interpreted similarly to Pearson's R. Kramer's V measures the association between two nominal or categorical variables, especially when one or both variables have more than two categories. Unlike Pearson's R, its value ranges from 0 to +1 and it does not indicate the direction of the relationship. However, the general interpretation of the magnitude of the effect is similar to that of Pearson's R. An odds ratio is the ratio of the odds of an event occurring in an exposed group to the odds of the event occurring in a non-exposed group. This value measures the association between two binary variables, specifically between an exposure or intervention and the occurrence of an outcome or event. For instance, if the odds ratio for smoking and lung cancer is 2.0, it means that the odds of smokers developing lung cancer are twice the odds of non-smokers developing it. These are commonly used guidelines for interpreting the odds ratio. While the relative risk is the ratio of the probability or risk of an event occurring in an exposed group to the probability or risk of the event occurring in a non-exposed group. For instance, if the relative risk for smoking and lung cancer is 2.0, it means that the risk of smokers developing lung cancer is twice the risk of non-smokers developing it. These are commonly used guidelines for the interpretation of relative risk. If you'd like to test your knowledge on this topic, be sure to check the quiz link in the description below or visit our community page.